Your warm-up question for today says, based on its free body diagram, what can you tell me about the motion of this object? So this looks a lot like the free body diagrams you were looking at yesterday. What do I know about this object based on that diagram? I know that it has a net force of 3 newtons. Okay, yep, I know it has a net force of 3 newtons to the right. That's not so much about its motion. What does that tell me about its motion? It's moving, sure. What? Not necessarily moving to the right. What is it? What is happening to the right? It's accelerating to the right. Okay, it has positive acceleration. I don't actually know if it's moving to the right or not, but I do know that it's accelerating in the positive direction. Now, if it's moving to the right, that would mean that it would be speeding up because its acceleration would be in the same direction as its motion. But if it's moving to the left, it would be slowing down. And again, I don't know which way it's moving unless I'm given more information. Did you have a question, Annalise?
Yes, so we can say that it's moving to the right for the net force, but we can't for anything else.
The net force doesn't mean it's moving to the right. You would just say the net force is to the right. And you can say the acceleration is to the right. But no, you can't say anything else about its motion. Does anybody else have a question about this one? I could calculate its acceleration if I knew its mass. Okay, all right. So we're going to do a follow-up question here, and then we're going to get into some notes on friction and net force calculations, which is also the topic of your assignment today, 301.3. If you don't finish this assignment in class, it will be homework. It does only have 9 questions, but some of these are going to be trickier because they're more involved calculations with multiple steps. Okay, so this one is a follow-up to the warm-up. It says, which xt graph, or position time graph, could show the motion of the object in the free body diagram? You've got 3 choices, A, B, and C. Which one could show the motion of this object? B. The one that shows acceleration. Okay, B is exactly what the motion of this object would look like if it were moving to the right with that free body diagram. So if it were moving and accelerating, both of those in the positive direction, it would look like B. I couldn't pick A because A shows constant velocity. There's no acceleration in A. So in order for me to say that a free body diagram would give me an xt graph like the one in A, I would need to find a free body diagram where my forces cancel each other out, where I have a net force of 0. Then it could be A. By the way, in that case, it could also be C. Because again, if I have a net force of 0, all I know is my object isn't accelerating, which means either A or C could be true. It could either be moving at a constant speed or it could be at rest. Okay, so again, we are going to tie back in those graphs from the last unit as well. So that's another thing that may be tricky for some of you if you weren't too comfortable with the graphs. Okay. And that might mean that you have some extra studying to do in that case. The answer to this, though, would be B because this shows acceleration. It is the only one with a curve. This is just yesterday what we talked about. You can jot it down again, but you shouldn't need to if you already wrote it down once. But Newton's second law tells us that the acceleration of the object is dependent upon 2 variables. More specifically, I could say that the acceleration is going to be directly proportional to the net force acting upon the object and inversely proportional to the mass of the object. And that is summarized by the equation F net equals ma. So in the warm-up question, because we had a net force, we also had an acceleration. That acceleration was in the same direction as our net force. Okay, so again, tying this all together. And guys, by the way, if you've got a phone out, let's go ahead and get those put away. You really do need to jot down some notes today, Drew. Okay. All right, let's look at this example. A rightward force of 5 newtons is applied to a 2-kilogram book to move it horizontally across a desk. The force of friction between the book and the desk is 1.5 newtons. Find the net force acting on the book. You'll notice that I have already drawn in a free body diagram. And in my free body diagram, I have already labeled the rightward force that is applied to my book. It's right here, this red vector. I have already labeled the force of friction. Notice that I put the force of friction opposite the direction that the book is being pushed, and that will always be the case. Your force of friction will always be opposite the direction of the motion of the object. So if you're pushing something across the room to the right, your friction will be to the left. If you're pushing something upward against a wall and your applied force is up and your object's moving up, your friction will be down. Okay, it's always opposite the direction of motion, and it's always parallel to the surface that you're pushing it on. So like when I look at this book, for example, I have this flat tabletop, and so my friction will be directly, again, parallel to that. It's going to be directly to the left because it says that I'm pushing it to move it to the right. Okay, so that's how I labeled those. You'll notice I also have two vectors in my diagram that aren't labeled. A green one and a yellow one. The green one is going to, of course, be force of gravity. Okay, anytime you're on Earth, which you're going to assume that you're on Earth unless I tell you otherwise, okay, you're going to want to include that downward arrow for force of gravity. And if your object is moving on a surface, or if it's at rest on a surface, if it's on a surface, you also must include the normal force. And so that's what the yellow or orangish vector is representing, is my normal force. You should also notice that I drew them in such a way that they have equal lengths. And I did that because it says this book is just being moved horizontally. It doesn't mention anything about my book having vertical motion. And if I don't have vertical acceleration, okay, of course, if I'm not moving vertically, I wouldn't have that, then I know that those forces have to cancel and my net force has to be 0. So I drew them to show that as well. I could label them. I don't have numbers to put on them, although I could actually solve for those, which I'm about to do. We're going to find the net force acting on the book, and like I said yesterday, when you find net force, you have to do it separately for the horizontal and vertical directions. Now I'm going to start with the vertical because I already know that my vertical direction is going to cancel. But I didn't put the numbers on here, so let's do that. F sub g, my green vector, is mass times gravitational acceleration. That is 2 times negative 9.8, and it is equal to negative 19.6. Again, the 2 came from the question, 2 kilogram book. Okay, so there is my force of gravity. And again, just like we mentioned a second ago, Fn is going to be equal and opposite because my book does not have vertical acceleration or even vertical motion at all. So I know that these two forces are going to cancel each other out. If this one is 19.6, this one is also 19.6. This is negative, this is positive. My net force in the y direction will be 0. Okay, now, a lot of times we don't bother even working out the net force in the y direction in a scenario like this when we know that they're going to cancel. You don't really have to necessarily write out those steps because you already know that it's 0. And we tend to just focus on the one that we know is unbalanced, in this case in my horizontal direction. Again, net force is the sum of all the forces acting on the object. In this case, I have Fa is 5 newtons. That's my applied force. I have FF is negative 1.5. Again, these are vectors. If it's pointing to the left, I'm going to call it a negative number. If you forget that, you're going to get the wrong answer when you find your net force, because when you add them together, it's 5 plus negative 1.5. It's truly a subtraction problem at this time. And 5 plus negative 1.5, or 5 minus 1.5, is 3.5 newtons in the positive direction. Again, I can see that looking at this. This number is 3.5 newtons larger than this one. Okay, and so my net force will be 3.5 newtons to the right. And again, that's the direction. The direction of the net force is going to be to the right because 5 is bigger than 1.5. Thus, the acceleration will also be to the right. We talked about this yesterday. What direction does it accelerate? The same direction as the net force. If the net force is to the right, so is the acceleration. This should be a kind of recap of yesterday before we start to add in some new stuff. But does anybody have a question about this before I move on? Okay. Let's try this one. You'll notice here I didn't even bother labeling the vertical forces because I'm going to assume again that this box is accelerating across a floor, and so I don't really need to care about the vertical ones. in this example, although usually we draw them in our diagrams because you might need it for a calculation of some kind, which you'll see later on. But for this one I don't, so I didn't bother drawing them. It says a 2 kilogram box accelerates 12 meters per second squared to the right. What is the net force acting on the box? And then I have a free body diagram with one force labeled as 3 newtons and the other one is S. I don't know what it is yet. Okay, but I actually don't need the diagram to solve the question. Okay, the question already gives me a mass and it already gives me an acceleration. If I know the acceleration and the mass of the object, I can solve for net force using the same equation we learned yesterday. F net equals m times a. Plugging in, I have a mass, I have an acceleration. 2 times 12 is 24 newtons, and my net force will be in the positive direction because my acceleration was also in the positive direction or to the right. Okay, so my net force, 24 newtons to the right. Okay, so that one's simple enough. The picture might even throw you off if that's all you were asked for. However, that's usually not what I'm going to ask for. Instead, what you're going to see is a 2 kilogram box accelerates 12 meters per second to the right. What is the force S? This is the harder question. Because now I'm not asking you for the net force, I'm asking you to solve for this unknown force that's labeled with an S. Now, if you find the net force first, which I just had you do, this is easier. Because I know that net force is the sum of my forces. So I know that my net force in the x direction is all of my rightward forces plus all of my leftward forces. Okay, and since I already found net force and I already know the only other force to the left, I can plug in. 24 equals S plus -3. If you forget that negative sign, you're going to get the wrong answer. Again, if it's in the negative direction, label it with a negative here. If I now want to solve for S, I'm adding a negative number. If I subtract that negative number from both sides, then I'm really adding 3 to the other side, and I get that S is equal to 27 newtons. Again, when you see this type of question on a test, on a quiz, or even on your assignment today, it's not going to ask you to find the net force first. It's just going to say, hey, this 2 kilogram box accelerates 12 meters per second to the right. Based on the free body diagram below, what is the force S? And it's up to you to look at that situation and say, I don't know how to find force S, but I do know how to find net force. And if I find net force, then I can find force S. You're going to have to go through that thought process. Okay? And that, by the way, is not unique to this unit. That is all year long. There's a lot of times when you're going to have to look at what you know and you're going to have to say, what can I do with this? What can I figure out? How can I get to the answer to this question? Okay, so that's the hard part here. The math itself, that's easy. Once you actually figure out what to do with it, the math is not hard. It's figuring out what to do with those numbers and how to use them to get here. Does anybody have a question about any portion of this problem? Not at this time. Okay, maybe you will once you try it on your own. We'll find out. All right, so here's a follow-up question. So I know this object accelerates 12 meters per second squared to the right. I know the net force is 24 newtons to the right. We found those on the previous slide. I went ahead and labeled the mass. I even labeled S. Okay, so I've got all my information. And this time the question says, if this box is moving to the left. Again, I didn't know that before, but now I do. If this box is moving to the left, will it get faster, slower, or have a constant speed? Yes. Slower. Yeah, it will get slower because if the acceleration is in the opposite direction as the motion, you will slow down. I know my acceleration is to the right. I can see it in the diagram. I also have it right here, 12 meters per second squared to the right. I know my acceleration is to the right. If this is moving opposite, left is opposite, you will slow down. Okay, so if your acceleration and velocity are in opposite directions, you will slow down. This is from the last unit, but you might need to write it down anyway, especially if you struggled with this last unit. I even put some fake numbers up here to help you see what that means. Here is an object that is moving to the left. Again, left is going to be negative, so I have a velocity initially of -10. Okay, and if I have positive acceleration, that means that the change in this velocity is a positive change. So I went from negative 10 to negative 8, that's a change of positive 2. To negative 6, that's still positive 2. To negative 4, and I could keep going if I wanted to. But this is what those numbers would look like. Negative 10, negative 8, negative 6, negative 4. This is slowing down. We're getting closer and closer to 0. And if we get to 0, of course, we have stopped. Okay, so this is what that would look like. Okay, on a data table. What would it look like on a graph? On a VT graph specifically? Let's start with 2 questions that we need to answer. Would I need to draw my line above the x-axis or below it? Below. Because it says the box is moving left. That's negative. And even if I look back here, look, negative 10. That's just an example number, but it's still down here. I have to start down here. Okay, and when I do that, I'm going to start down here, and I need to slow down. I need to move towards 0, and so your graph would look something like that. This, of course, shows it moving all the way to a stop. If it didn't stop, it wouldn't go all the way to 0, but that is the shape that you're going to need to get. If you struggled with these graphs last unit, you need to review them because you need to be able to interpret them to answer questions like this one. Does anybody have a question about that graph? If you need to make notes about the graph, remind yourself, if I have a negative velocity, if I'm going backwards, I'm below x. If I have a positive velocity, if I'm going forward, I'm above x. If I'm slowing down, I move towards 0. If I'm speeding up, I move away from 0. Okay, those are the kind of general rules from last unit.
Are we just going to see VT graphs?
Not necessarily. I did an XT graph earlier in the warm-up, right after the warm-up. All right, let's try this one. If the object below has a mass of 0.3 kilograms, what is its acceleration?
0.
Yeah, I didn't have to do any math. Look at that free body diagram. It has 0 net force on it, therefore your acceleration is 0. Which XT graph might show the motion? There's your answer when you asked. A, sure, A could show it. B could show it. Again, I don't actually know if this object is moving or not. It could be at rest, that's 0 acceleration. It could also be moving forward with a constant speed, or for that matter, backward with a constant speed. Again, we don't know. But all we know is it's not accelerating, so don't pick a curve on your XT graph. Questions about this one? All right. This question says, find the force of tension in the cable if the wrecking ball has a mass of 500 kilograms and is hanging at rest. I'm going to ask you all right now to go ahead and draw a free body diagram for this. We practiced that yesterday, but see if you can draw a free body diagram for the wrecking ball. That's going to help us to answer this question in a minute. So think of what forces are acting on it, what direction they are, and see if you can draw it. I'm going to give you 27 seconds. You can turn and talk to your neighbor if you're not sure, but please draw a free body diagram for the wrecking ball. Okay, maybe you finished it, maybe not, but let me ask you this. What forces do we need to draw? Tension and gravity, perfect. Okay, if you didn't come up with that, that's okay, write it down now, but we need to draw tension and we need to draw gravity. Okay, you'll notice, here's what mine looks like. Here's my wrecking ball, here's my tension, here's my gravity. You'll notice I drew them the same length, and I even marked that they're the same length. I know you guys use these marks to show like congruent sides in math. I'm going to use it to show congruent or equal magnitudes of force here. Okay, so I have an equal amount of tension as gravity, and I did that because the question says it's hanging at rest. And if it's at rest, my forces have to be balanced, or if it's a constant velocity, either way, but this one says at rest. So I went ahead and drew it so that Ft was equal to Fg. Okay, so now let's revisit the question. Find the force of tension in the cable. Guys, I don't have an equation for force of tension. However, what do I have an equation for? Fg. If you find force of gravity, that is your force of tension based on the diagram we just drew. Okay, so we're going to solve for force of gravity, and that will also be equal to your force of tension. Force of gravity is mass times gravitational acceleration. That's 500 times 9.8. You'll notice I dropped the negative. That's because I'm really just looking for the magnitudes here. Okay, I know that one's up and one's down. But 500 times 9.8 is 4,900. So my force of tension is 4,900 newtons up. My force of gravity is 4,900 newtons down. Okay, but it wants to know the tension. So my answer is just 4,900 newtons up, or positive 4,900 newtons. Questions about this one? Not so far? Okay. All right, so friction. I told you we're going to talk about friction today. Friction is caused by one surface moving over another. It is a force that can resist the motion of an object. It can prevent an object from moving, and if you park your car on a hill, you are banking on that. You're like, I sure hope the friction between my brake pads and my rotors and between my tires and the roadway is enough to keep my car from rolling down this hill. Okay? You are banking on friction keeping you where you're at. It could also slow an object down. If I was to, push a chair across the room, it will roll a little bit, but it will of course slow down and eventually stop due to the friction between the wheels and the floor. But regardless, it always opposes the motion or desired motion of the object. You guys are going to want to write down that sentence. If nothing else, please write down that friction always opposes the motion or desired motion of the object. And by that I mean, for desired motion, if you right now try to push your desk, not hard, just push it a little bit. It's not going to go anywhere. Okay, you're pushing forward, the desk, or the friction rather, is pushing opposite that. It's backward. That's what I mean by desired motion. Okay, it's going to oppose that motion or the motion you're trying to create, okay, or the desired motion of the object. Now, the amount of friction present will depend on two different factors. The types of the surfaces interacting, whether they're smooth or rough, okay, is going to play part of that role. And then the normal force, and that's that force of contact between them. So if there's a lot of support force there, if there's a lot of contact between the two, you're going to have more friction than if you have less of that. Okay, so it depends on those two things, and we can see that in an equation. This is the equation down here at the bottom. You've seen it before in our notes on the first day, but it's force of friction equals, and this Greek letter is called mu, M-U, but it represents the coefficient of friction. The coefficient of friction tells us how smooth or rough the surface is. Okay, so a low number is going to be a really smooth surface. The higher that number, the rougher or stickier or whatever word you might need to use that surface is. Okay, and then the normal force. We do have two types of friction, static friction and kinetic friction. So that static friction is the force that keeps the object at rest. So if I push my desk a little bit, which I'm doing right now, it's not moving due to the static friction between my desk and the floor. Okay, but if I push it hard enough and I overcome that static friction, which of course we can do, we can push harder. If we overcome that static friction, the friction is still acting on it. It's just now called kinetic friction, and that's the friction that's going to slow down the moving object. If I push the chair or push the desk and I overcome its static friction, then now it's moving. The friction will eventually cause it to stop. But again, friction depends on two things: the type of surface, how slippery or smooth or rough it is, that's mu, and the normal force. I did put here mu is always less than 1. That's not technically true, but the numbers we're going to use, mu is always less than 1. Like if you had like Velcro, it's not less than 1 anymore, like if your substance is actually pulling on the other. But for most of the examples we're going to do, it's going to be less than 1. Therefore, mathematically speaking, force of friction will be less than normal force. All right, let's try this example. It says, a 5-point Newton duster is pulled rightward across a desk with a force of 5 newtons. If the coefficient of friction between the desk and the duster is 0.1, what is the frictional force? What is the net force? Okay, we're going to start with a free body diagram. Okay, so looking at the question, I am told that I have a 5.8 Newton duster. We had wording like this yesterday, a 14,700 Newton car. I told you if it's worded like that as like a property of the duster or a property of the car, that is the weight. Look at the units. Newtons is force and weight is a force, so that's the weight. They gave it to me. I don't have to calculate it, it's in the question. 5.8 newtons is the weight. Now, because we're pulling this across a desk, we have a surface that's going to push back with a normal force, and this question doesn't mention anything about my duster accelerating up or down, so I'm going to go ahead and say that I also have a normal force of 5.8 newtons upward. I want those to cancel. I want a net force of 0 vertically, based on the wording of the question. The last thing that I see in terms of forces is that it's pulled rightward with a force of 5 newtons, so I'm going to draw my 5 newtons to the right. I do know that there is friction because it's implied when it says what is the frictional force if this is my coefficient. Also, I know there's friction because my coefficient isn't 0. Okay, I don't know how much friction there is, but I know it's there. I will mention this, and you can write this down as well, but the force of friction will always be either less than or equal to this applied force. So my force of friction can't be more than 5. It could be 5, okay, and that of course would mean that my duster was either moving at constant speed or not moving. Okay, it could be 5, but it can't be greater. There's no such thing as having friction greater. It opposes the motion, and so it's always either less than or equal to. So I drew my arrow shorter, but it could technically be the same length. I don't know without calculating it. So let's label our givens. I know the force of gravity is negative 5.8 newtons. I can see in the picture that it's negative, so I went ahead and labeled it negative. I know Fn is positive 5.8. Again, I can see that it's upward, so I went ahead and labeled it positive. I know my applied force is positive 5. I know mu, my coefficient of friction, is 0.41. It's in the question. And guys, don't put this as a force. Coefficient of friction isn't the force of friction. Different thing. And by the way, the coefficient of friction has no units. Okay, it's just 0.41. It's like a ratio, kind of. All right. We are looking to find friction. So let's start with the friction equation. Force of friction is mu times Fn. I have mu, I have Fn. Notice though, they did not give me Fn in the question. I only figured it out because I drew my diagram. Okay, so that's why it's so important to draw that diagram and to think about all those forces. Plugging in, that is 0.41 times 5.8, which gives me a force of friction of negative 2.378. Anybody know why I labeled it negative? Because it's opposing the direction of the motion. You'll notice the math itself doesn't give me a negative number. But I looked at my diagram and I said that's opposite direction as I'm going, and if I'm going positive, my friction will be negative. So I went ahead and labeled it that way. Yes, sir?
So in this free body diagram, can you tell which direction it's going?
I can. If friction is labeled on my free body diagram, I can tell what direction my object is moving because friction will oppose its motion. It also says it's pulled rightward across the desk. Okay, but yes, if you have friction labeled, you can tell. All right. So my net force is 5 newtons plus negative 2.378. Again, that's these two horizontal forces. I don't have to worry about calculating this. I'm not going to waste my time. I can see it's 0. So I'm just going to do F net in the x direction, keeping in mind that my friction is negative so that when I add, I'm really subtracting. And I get a net force in the x direction of positive 2.622 newtons. Okay, does anybody have a question so far about how I got that number? Yes, ma'am.
Where'd you get the equation from for F net x?
F net is, by definition, the sum of all of the forces in the x direction, in this case, acting on the object. So F net, you're going to do F net x and F net y separately. I didn't bother doing F net y because I can tell it's 0, but you could technically have done the same thing there. Did you have a question in the back? No? Okay. Any other questions? All right, let's try this one. A large block of ice is being pulled to the right across a frozen lake. The block of ice has a mass of 250 kilograms. The coefficient of friction between the two ice surfaces is small. Mu equals 0.05. By the way, if mu is 0, it is frictionless. Okay, so this is a very small number. What is the force of friction that is acting on the block of ice? Okay, so again, we can start by labeling things, but I'm going to tell you right now, you're going to want a free body diagram eventually. So you might want to try to draw one now, but I'm going to label a couple things first. My mass is 250 kilograms. Mu is 0.05. And those are the only numbers given to me in the question. So let's see what we can figure out. Okay, I know I'm going to need force of friction. I know that means I need mu times Fn. I don't have Fn. So again, let's try this. Let's draw the free body diagram and see what we can figure out. Okay, if you draw the free body diagram, actually take a second and see if you can draw one. Okay, talk to your neighbor if you're not sure. You've got like 18 seconds. See if you can draw a free body diagram for this situation. Okay, free body diagram. Maybe yours looks something like this. If not, draw that. Okay, I have force of gravity downward. I have normal force upward because it's being pulled across a lake. There's a surface there. Okay, so I'm going to have normal force and force of gravity. I'm trying to draw them so that they're roughly equal in length because my question mentions nothing about it accelerating up or down, so I'm assuming those are balanced. They're going to cancel. Okay, and so the other forces I have are force of tension because he was using a rope. If you labeled it applied force, that's fine too for this scenario. And then force of friction. I'm assuming it's small because it tells me that it's small. Okay, so I drew that arrow shorter. From here, again, ultimately this is what I need to do. I need to solve for force of friction, which means I need Fn. I don't have an equation for Fn. How do I find it? I have an equation for Fg, and they're the same. Okay, they're the same magnitude. Fn is equal to Fg. Fg is equal to mass times gravitational acceleration, which in this case is 250 times 9.8. I'm just looking for the magnitude here so that since I already have the directions labeled in my picture, my normal force is 2,450 newtons upward. Thus, my force of gravity is 2,450 newtons downward. Okay, so I have Fn now, and now that I have Fn, I can find Ff. Mu times Fn, 0.05 times 2,450, gives me 122.5 newtons. That is your force of friction. Okay, so that is how you would solve this particular question, although I'm going to give you a follow-up question in just a second. Okay, does anybody have a question about this before I move on to that next part? Okay. All right, so we just found the force of friction. By the way, once you find the numbers, go ahead and label them on your diagram. You'll notice I have added all the numbers to my free body diagram. If you're answering subsequent questions, this might come in handy. So I have Fn, I have Fg, I have Ff. The question now says, if the acceleration of the ice block is positive 2.5 meters per second squared, what is the net force on the ice block? Okay, well, net force I can either find if I know all the forces in my diagram, I can find it that way, but I don't know them all. So instead, the other way to find net force is with the equation that we've been using, F net equals ma. Do you have a question? No? Okay. So we're going to multiply 250 times 2.5. That will give me my net force, which will be equal to 625 newtons to the right. Again, it will be in the same direction as my acceleration, which was positive, thus this is also positive. Okay, so 625 newtons to the right. That's the first question. The second question says, what is the tension force pulling on the ice block? Well, once I know the net force, I can find that because I also know the force of friction. And I know the net force is the sum of the forces acting on the object. By the way, it's down here now, net force 625 to the right. And so because I know that my net force is all of those rightward forces plus all of those leftward forces, keeping in mind that the ones to the left are negative, I can solve for Ft. So I have my net force 625 newtons equals Ft, that's what I'm trying to find, plus my force to the left is friction, and again I tacked a negative on because it's to the left, plus negative 122.5. If I want to solve for that, I need to move that negative 122.5 to the other side, which means I'm subtracting a negative or just adding a positive. 747.5 newtons to the right. Again, when I saw this net force, I already knew Ft over here had to be 625 newtons larger than 122.5. Okay, so you could do it logically or you can go back to that equation. Either way, you're going to get 747.5 newtons to the right. Yes, sir.
So the force of tension is equals the net force plus the force of friction?
Yes, plus the negative.
Yeah, the negative.
Yeah. Well, it ends up being subtracted by the negative, so you're, yes, that is what you're doing. Any other questions? Okay. Then let's see if you have questions when you try it on your own. Please make your way to My Open Math. You're looking for the assignment 301.3 friction and net force problem set. I'd like you to get as much of it done in here as you can. You guys have about, I can't even do math right now, 13 minutes. Okay, you have 13 minutes to work on this. So that should be enough time to get through a couple of them. I think the math is more toward the end. If you want to skip and look at that part first, that's up to you. If you don't finish it in class, it is due by 11:59 p.m. tonight. And guys, please have out paper. You need to draw free body diagrams. You need to label things. You're going to want paper. If you have questions as you're working, please let me know.